Alô? Alô? Denis Severlin. He will speak about welding, and he's from University of Montpellier. Okay, so thank you for being here, Professor Denis. Also,
thank you very much for the introduction. So I want to talk to you about welding basics. I want to say basics and introduce how is welding. What about welding? That's the first question we can have. Welding is everywhere. You can imagine a world without welding. Barges, ships, airplane, pipes, trains, automotive, tank storage, home appliance, bridges, building, ornamental ironworks, construction. You are sitting on a welding system. You take with your head on up and you see welding structure. Welding structure is everywhere. But it's so common that everybody thinks doesn't exist. And welding is very interesting because we're welding steel. And steel is 100% and infinitely recyclable. And in a world which we talk about Green Deal, where we've got societal responsibility, sustainable, welding is everywhere. Everywhere. And for just an example, if we talk about sustainable development of United Nations, there is 70 points. And in these 70 points, you can find more than 10 points where welding is present. For example, zero hunger. How can you make zero hunger without agro-food? Agro-food is piping, is capacity, is tanks, etc. When you talk about health, pharmacy, medicine, how can you make vaccines without welding? It's impossible. When you talk about water, you need pipes, and pipes is welded. When you talk about energy, we talk about energy after, but energy without welding is impossible. Industry, it's normal, I don't speak about that. Civil construction, engineering, all is steel, all is welded. New energy, climate action, manufacturing, transport. Life below water, below water. You have pipes, you have submarine, you have ships. We are everywhere. Everywhere is welding. Industrial presser and vessel company are aware of the key environmental issue in which to actively participate in the deployment of industrial solutions that will allow the objectives to be achieved. Okay. Mobility, when you talk network design, installation of storage, drying compression, slow charging, quick charging, connection, distribution terminal, all is welding. You talk about gas, biogas, new gas, and so on. You have to talk, you have to tank them. You need skid, you need, I don't speak about hydrogen. Everybody said the new generation, the new power will be hydrogen. Hydrogen, high pressure, low pressure pipes, storage, drying equipment. You talk about solar. It's good to talk about solar, but to put your solar, you need structures, and structures is welded. Wind turbine is welded. And I finish by what we like in France, nuclear plant. A nuclear plant, what is it? It's a big steam with pipes, with turbines, with all is welding. So welding is everywhere. We can talk about story of welding. Welding is very old. In 2000 years before GC, we talk about welding Bronze Age. People began to make parts together with Bronze Age. Egyptian and people is learning piece of iron together. During the Middle Age, we began to talk about that. But the real story of the welding is until 1991, Charles Picard, a friend, knows work in gas welding. It was process is combination of oxygen and acetylene. At the same time, Edouard Fouché, a friend, again, engineer and inventor, developed an oxyacetylenic welding process. In 1998, Oskar Kjellsberg, a Swedish, has the first patent to weld with electric arc. And it's a shame, but World War is always time to develop new technology. And during World War, new welding production were made. Many companies trying to manufacture welding machine, electrode to make equipment. From 1920, French Institute, Welding French Institute, is working on development of welding. The first welding job was introduced in 1931, less than 1 century. It's very young. 1932, submerged arc welding. Around 1950, the new process. And the new technology is after 2000, it's very recent, with development of electronic and miniaturization with data system. At the same time, and that is very interesting to think, we develop an international institution of welding. What is it? In 1948, people from different countries said, we have to work together with welding. And they began to develop an international institution of welding. And in 1963, there was the first publication of a review whose name is Welding in the World, Soudage dans le Monde. At this time, at this beginning time, this review was in 2 languages, French and English. After, in 1992, with Europe, with development of Europe, it was extended from many countries in Europe, and in 2000, this International Institution of Welding was over around the world. And today is more than 34 active NBS. NBS is Authorization National Board. Is country who is authorized to make training in welding following this program. And more than 17 countries belong to this system. That means that Welding, International Institute of Welding, apply an international program, and this program will be in a country. In France, we have Association Française du Soudage, is an association who take a program from training international and who translate in France. In Brazil, you have Associação Brasileira del Soldagem. I don't speak Portuguese. It makes the same one. And there is 3 levels of training. IWS, International Welding Specialist. What is it? He's a welder who knows a little of technique. The second level is International Welding Technologist. Is a technician in welding, specialist in welding. And the third level is IWE, International Welding Engineer. The 3 levels are recognized by the IIW, and in Montpellier, in University of Montpellier, we are lucky because we have two levels. We have engineer masters IWE in Polytech, and we make welding engineer. The students follow a training, and after they pass this certification, and they can be welding engineer, and they can be welding engineer around the world. You have a Chinese, Brazilian, or something who has the same diploma. You're sure that he has followed the same training. IWT, we have in University of Montpellier too, technician, and we make the same program. And the two girls come from Polytech, make last year IWT program. That is very interesting to show that welding today is around the world. And we cannot say we are Brazilian and we weld in Brazil. We are French, we weld in France. We are around the world. It's a globalization. And it's very interesting to see that a system is globalized. So, after that, we want to come back to the welding. What is the welding? The welding is a joining process. A joining process like new bolts, screwing, rivet, casting, brazing, glue, resin. What is the difference with welding? Welding has made speed possible. Has made speed possible. Why? Because we have a physical continuity, material of the same nature. We have an homogeneity of mechanical properties. And we assemble how is made welding by assembly process by localized fusion of the edge. That is the definition. We assemble by localized fusion. Localized fusion, when you talk about fusion, you talk about heat. And the base of the welding is a heat source. You have different type of heat source. It can be mechanical, it can be chemical, and the most of the time it's an electric source. Some of you are maybe chemical, and you know when you have a steel and when you make high temperature, you have an oxidation. Oxidation with the oxygen of the air. So you have obligatory a protection mode against the effect of the air. And the two first points are theoretical. You have two pieces, you have heating, you have mode of protection. But when you think as mechanician, it's very difficult to have two pieces exactly one together the other. You have always, or fast always, gap between the two pieces. So you have to put a filler metal more. If the filler metal is the same or the same as a base metal, we are talking about homogeneous welding. When the filler metal is different, we are talking about heterogeneous welding. I made a slide about health and safety in welding. When we talk with heating, very hot temperature, it's burning. You have risk related to fume. When you are welding, you melt metal, you have fumes, steam of steel, of iron, of different metal, and it's dangerous. We want to use shielding gas. When you use shielding gas, there is a risk of anoxia. When you have metal, high temperature, most of 1,000, 1,500 degrees, you have risk of projection and hot part. When you have arc, you have optical radiation. You have noises. When you use electricity, you have electricity risk, electromagnetic fields, and fire and explosion. So people who use welder have to be protected. And you see on this picture a minimum with gloves, with helmet, with and so on. Now I want to talk to you about consequence of welding operation. When you want to weld, you have to make high temperature. You have to be in expansion and shrinkage. At low thickness, high strength, but stress area. At high thickness, little deformation, but very, very, very high stress. Because you don't have deformation, but the deformation inside the metal, and you have big stress. For that, often, after welding, we have to make a heat treatment after welding. We have to make high temperature to make to low residual stresses. That is the first point. The second point is a modification of the metallurgic structure. When you make a steel high temperature, you change the structure. For steel, iron steel, you pass from FCC to CFC. So you have modification of modification structure. And the first part is easy to understand, but we have to think about that. I said welding, you melt metal. When you melt metal, it will be liquid. And the liquid, you want to fall. And the big difficulty by welding is to maintain this part of metal who be liquid. And these three parts are consequences for the operation of welding. For example, when you weld metal, base metal 1 and base metal 2, if you take big thickness, more than 3-4 millimeters, I say big, but it's not big, you want to have here laser point. You want to have here a metal liquid. If you take all this metal liquid with all this thickness, it will be very heavy. And too heavy, you have to fall and you have to make a hole. So you have to prepare here with a chamfer here. You have to prepare. We want to make one roots weld, and then we have to make more weld. For example, here you have a roots here. The preparation was like that. You make a roots here, and then we make different paths to fill it. In this case, the root is here, and you have here 1, 2, 3, 4, 5, 6, 7, 8. 8 paths one side and 2 paths the other side. If you are thin, thinner than 3 millimeters, one path is enough. We call about monopath welding or multipath welding. That is an example of penetrant roots. And second point, the thermal aspect of the welding operation. When you weld, if you take a thermocouple, you can measure the temperature. When you weld in a point, you have temperature grow up and then fall down. Here, you grow up here here, by definition, higher than the melting point. So here, the time between 800 degrees will be very important, because if this time is very short, you have a risk of martensite. If the time is low, you don't have this risk. And here, when you weld, you have here the welded zone. By definition, this welding zone is higher than 1500 degrees because we melt it. Here, far away from the welded, you are in normal temperature, but between here, you have a zone who name heat affected zone. It's a zone in which we are higher than 900 degrees, and we had, for the steel, the iron steel, we have a change of temperature. We have stress in here, for example, you can see the molten zone pass 1, the molten zone pass 2, and here in two sides you have a heat affected zone, the zone in which the metal was transformed. And if you take a steel, a low carbon steel we use in welding, you see that at this time you go up here in austenite phase, and if you cooling rapidly, you can have a risk of cough quench. So here, don't forget melted zone, and each side of the melted zone you have a risk of quench, and it could be very different. When you weld, you have stress in welding. I say you have deformation, and during the welding you have different stression, compression and traction, and that will make deformation or stress inside the weld. So when you weld here, you have a melted zone, and at the part of the welding zone you have different structure of welding. What is important? First part very important is the welding energy. If you put most energy, if the energy is high, for example here, if the energy is high, the pieces hot temperature inside, and the cooling will be low. If the energy is low, it will be cooling very fast, and you have a risk of quench. So the heat input during welding is very important to show the risk of quench. For example, here, if you are two pieces, the cooling will be here. If you are this kind of welding, you see that the cooling will be here, here, and here, and there will be more risk of quench than light. Okay, and often to prevent the problem of quench, what we have to do a preheating. We want to preheat the piece before welding to prevent the risk of quench. For example, here you have three parts. Here is a butt welding with tubes, and here you see that this kind of welding will cool it very speedily than this. And maybe for this you have to make a preheat, and this you don't have. By conclusion, what I want to say that welding, generality of welding you have to big energy to melt the steel, and many consequences are we. And with this consequence, we have deformation, for example that. For a piece along we have compression traction, we have this kind of deformation. And you have to prevent different method for the edge preparation or pre-deformation before welding, sequences for welding. When you weld a tube, for example, you have different, you don't make that, but you make 1, 2, 3, 4, and so on. You have to prevent, and you don't weld. When you have to weld, you have to think the consequence of welding. If you have any question, I'm here to answer. No questions? You made welding before? Yes? With Professor Ivan, maybe? Okay. So you know what I explained. Okay.
Any question?
No question? So if you don't have question,
Thank you. I learned lots of things. Question, the origin of energy, and we know that it can be optical, like you can hit with laser.
yeah,
You
for
didn't-
example,
You didn't mention it because it's
You
just
have-
a small
you have
amount of welding.
five big kind of energy. Electric energy, two parts with arc, 80%, part with Joule effect. That is electric. You have chemical energy with gas mixed of acetylene and oxygen or different gases. You have mechanical energy, for example, friction or friction stir welding. You have friction and mechanical energy, put this energy to weld. And the fourth is what we name high density of energy. What is high density energy? We have two big processes, laser and electron beam. The principle is, to give an idea, for a classic process, you need 2-3 kilowatt for 1 square millimeter. For a high density of energy, you have the same energy, 3-4 kilowatt, but not for 1 square centimeter, but for 1 square millimeter or 1/10 millimeter. Very, very, very slow, very little surface. And for that, the penetration will be very high and deformation are very slow because you affect only a small zone. The consequence is, I told before of the preparation, and I told about gap. When you have an electron beam or laser who is 0.1 millimeters, you have to prepare the pieces better than 0.01 millimeters. But if you don't have that, the laser go through. And you make different preparation and different consequences. And it will be very, very expensive from preparation.
Thanks. So it's specific application, and it's a small amount of all the weldings that
Yes.
are made in the world.
High density of energy is 1 or 2% of welding now. It's very more than 80% of welding is arc welding.
I have one question.
Yeah.
For the formation, engineering, technologists, and specialists, what's the difference? Is the practical or the
No,
theoretical?
the difference is many parts. The number of time. Specialist is 250 hours. Technologist is 350 and engineer is 450. The three parts are divided in 4 parts: process, metallurgy welding, design, and quality. But the big difference is the number of hours and the detail until we go.
Yeah, and brazing is not a welding process, is another one. So sorry, I'm not
Oh.
from engineering.
Brazing is not a welding process as welding, because the definition of welding is we have melted material. In brazing, we have melted only the metal, the consumable metal. Okay, and you have diffusion of this consumable metal in the base metal, and the base metal is not melted. Is that the difference?
Merci.
Is just a curiosity is right about with the case of Naira. If I understand, so the diploma of weld engineering
Yeah.
is a kind of second engineering and title. Is that?
Yeah.
Is not the only one. I mean, the student gets another title of engineer, or just the welding
It's
engineer
not,
title.
it's complicated. It's not an engineer diploma. It's an engineer certificate. But we included that in our formation, and a student have, for example, for IWT, they have a license in web, and with this license, they become certificate of IWT.
So this girl, for instance,
Yeah.
you're doing a formation in mechanical engineering or something like this. Is that? You are, when you finish your formation, you get the engineer title of mechanical engineering. Yes, with specialization, certification in welding.
Yeah.
I see. Okay.
That's not everywhere, because,
No, yeah.
for example, in the United States there is Colorado School of Mining that you have weld engineers, and there
Yeah.
are some people, yes, some place in the world you have weld engineers. I think mainly for undeveloped countries is not a very good business, because
Yeah.
you need to have different things to do in your life.
It's for that we have made the choice we have made in Polytech Montpellier. We made a mechanical engineer in pressure and vessel manufacturing, and after, during 1 year, they prepare welding engineer. Some of them could be engineer, mechanical engineer, and welding engineer, and some of them are only mechanical engineer. And in Polytech, for example, in another Polytech, they made engineer in material, and this material engineer could have welding engineer after. Okay, thank you very much for everybody, and now let's speak to Ivan, my friend.
I agree with Dennis that we would have a conversation, and I show something about us, and after that I'll ask him some questions, because the title of my speech is exactly what we can learn from France about teaching welding technology. I'm in this business about 40 years now, more or less. I know a lot of people that work in many places with welding, in many countries. And the name of our laboratory, oops, what's happening? How can I go to the begin? Okay. Okay. Welding-related techniques laboratory. It's a laboratory that exists here in Campos do Vale, and I know that many people does know it, but it's a good laboratory. It was one of the first laboratories, welding laboratories in Brazil, and the name of it, we have another 3 people who work. Onde eu aperto para a luzinha? Here. 3 professors, Cynthia, Mazaferro, e Gonzalo, Rubem, that work. All of them were my students, MSc, PhD students. Cynthia was only undergraduate student, but and as those 2 knows very well welding technology, and we have in the undergraduate engineering, the name that I put about 40 years ago for our laboratory, welding related techniques, was copied from Sudage Technique Connects, the first review journal that I read about welding technology. And I am an admirer of Professor Granjon, that has founded many things in welding in France. I don't speak anymore French, it's a bit, but I could in the past read French and speak a little. Nowadays I forgot, and some words I exchange with Danish, but I'm terrible in French. So many years I tried to have some relationship with French people in technology, but I think now it is the opportunity to have this relationship. I think if you drink and dinner tonight, the relationship is closed. It's done. I'm sure we done that. We'll do that. And for undergraduate engineering course here, that is given to mechanical, metallurgical, and eventually for materials engineering, we have one class with 6 hours of welding technology. That's welding process. The students practice with weld, all welding process. They weld. They are, they know that. And welding metallurgy, of course, it's not very profound, but it gives the engineer an idea, and he or she can work on this technology and design of welded joint. Because, of course, you need not only to weld, you need to use weld for something, some structure or things like that. And that is very important under my point of view. So the discipline is taught with theoretical and the practical classes for everybody. 4 classes with maximum of 20 students, and we divide these 20 students in 4 or 5 groups that weld. And the PhD students help to giving class to the undergraduate people. That is basically what we do in undergraduate course. For the postgraduate level, we have 3 main classes. That is welding metallurgy, advanced process, and design of welded joint. Of course, we offer those class when we have students. Nowadays, we have few students. In the past, we had a lot of students in postgraduate, and that's the problem for us as well. I know that it's worldwide that problem, but that's true. We have all conventional welding process, those gas tungsten arc welding, gas metal arc welding, shielded metal arc welding. Everybody have seen this in the streets, some people welding. That is shielded metal arc weld, submerged arc, resistance weld, plasma cutting only, oxygas cutting and welding. Well, we have a small robot you've seen yesterday. It's good robot and very, very good power source. We had an extrusion press to make electrodes. We can make any kind of electrodes. And in our laboratory was made the first electrodes in Brazil to weld under what? Wet welding. You go up to 50 meters and weld wet, in contact with water. And Petrobras uses this nowadays. We had in the past very good relationship with Petrobras. In the last 10 or so years, we don't have a very good relationship for many reasons, and I don't want to discuss those things here. Well, it's a very expensive equipment, this one. That we talk about $120,000, things like that. A gas chromatography for diffusible hydrogen analysis. Dennis talked about cracking in the heat-affected zone and so on. One of the main causes of this is hydrogen in steels. Hydrogen comes from the covering of the electrodes or from the flux and things like that. And under the electric arc, that is the lowest temperature is shielded metal arc that's about 7,000 Kelvin, up to plasma arc welding with 30,000 Kelvin. The water dissociation and then ionizes. And then the atomic hydrogen goes to the melted metal and then go to the base metal. And if the base metal has some microstructure like martensite and things like that, that's not important for everybody now, but the fact is the thing happens and it's very dangerous. And with this equipment, we can measure that. And we had underwater welding, wet welding chamber. That was where we developed those electrodes. We have advice for photoelasticity stress analysis. It was built by an MSc student of mine that I lost for Petrobras before he finished. Well, good for him. Light microscopy, hardness tests, and so on. Okay, it's a basic laboratory with basically welding equipment and metallurgical equipments. I show that's the general photography of the laboratory. It's old one. That is the equipment for analysis. It's a gas. It's dedicated to analyze hydrogen only. That's for welding of tubes. We don't use much, but we can use for orbital welding. That's the robot. We have all necessary equipment to register the welding parameters, current, tension, temperature with thermocouples and so on. You see here, it is being registered. That's the one power source. We have many power sources. That is the extrusion press to make shielded metal arc welding. And that, for example, is one thing we developed some years ago. I developed with the PhD students. It's a absolutely new way to make plasma. It's a hybrid plasma torch. It has two stages. First, one plasma is formed, and then another stage. You have about, you see here, it's 20 millimeters here, 20 millimeters. That's 400 millimeters. About here, of course, it's highest temperature. It's about 30,000 degrees Celsius. It's very, very hot. You use it mainly for cutting or welding if you want. It's patented. Some Koreans, things like that, tried to buy for us, but it's too complicated to sell. Of course, the patent is of our university, but we are the, let's say, the intellectual, the intellectual properties, of course, are ours. And that was the chamber. They demolished it. It was a pit. Well, in the past, we used to weld for third parts different alloys that were difficult to weld in the past. Nowadays, there are many people that that pass through our laboratory know how to do things like to weld alloy, it's difficult, titanium, for example. And the other side of the river, Guaíba, for you that's not here, there are a big factory, a cellulose factory. It's a big one. And they use those valves, that's a valve. You have to, with time, the acids attack the surface of the valve. And then you have to weld all again. It's commercial pure titanium. You have to make a chamber with high purity argon. It's very expensive, this one. And weld during one day, thing like that. And that's one impact pendulum, a pendulum for performing structural impact. Here it's about 207 kilos that you can put up to 110 degrees. 110 degrees here. Yes, about that. That gives us about 9 kilojoules of energy. The impact is here. Did you understand? It's not Sharpie impact. It's a structural impact. You take a profile, welded profile, and impact it. And here I show you a luck mosquito. Here is the impact thing. It's not working. What a pity. It's mosquito news. I gave the number, the name of lucky mosquito here. It's flying. That was a piece, and then the pendulum impacted the thing. That's for millimeters. Well, we test also profiles. Profiles in mechanics or metallurgy are things like that. That's you see, you have a web here, and those are lines that was MSc dissertation. But our problem is with weldings here and here. Are you seeing the welds here? This is stiffener. We call it stiffener. It's good for, I think I will show. you're seeing in the side of that profile, and condition 1, yes. Look the deformation of the structure. Look the web here, the web is deforming. That's a high strength steel. That was taken at a rate of 7,000 frames per second. It's a high-speed camera. It's not ours. It's from the mechanical department. It can go up to 50,000 frames per second. Okay. And notice that this one is without stiffener. You can go. You can show the second. That is with stiffeners. Look the difference. It resists much more. Of course, our interest is on the welding, behavior of the welding. What we're noticing now is that it's much better to put there a more ductile weld than a more resistant weld. The problem is not strength, it's ductility. It's how to speak to people, for example, to have empathy and things like that. It's the same, ductility is the same. You have to have ductility, not to be very rigid. You have, yes, you have to exchange interests. That's the very interesting to notice in this. Okay, we're going to the end, and then I ask you some questions, okay? Okay. We had in the past, not now, but in the past we had some experience, well, some experience with fillet element analysis of mainly fillet welds, and you have a very good equipment there, computer equipment. It's another Professor Mazaferro works a lot with this. But this is mine. I did it. Only to prove the following. You do not can use finite element analysis in elastic. I'm lacking the word. You must use it in the plastic state. Why? Because if you do what I did here, you see that's the foot of the weld. You have tensions that impossible. Thousands of megapascal. And if you look that, you say, oh, the weld can't work in any structure. But it works. Why it works? Because it deforms. When it deforms, you have the tension lowers. That's the point. That's because fillet weld work. And this one are this phase of the fillet welding in photoelasticity stress analysis. You can look at those lines, and that's a convex face, and that's a plane face, for example. You see that a convex face, you have much more stress concentration in the foot of the weld. That's we show for the students as well, of course. Well, to finish, our very, very important things that we think now must be solved is, first of all, with all engineers, not only weld engineers. First of all, organizations and companies, every part of the world, must work SAS. That is, Siberia, Amazons, and Sahara. Understand? In the desert of Sahara, in Siberia, and Amazons. I mean, different places, different uh, uh, temperatures, different levels of humidity or moisture, and things like that. That's an important point. The second point is that our engineers in general don't look for unexpected loads. They make wrong predictions. They believe too much, I think, in mechanical tests and so on. Too much. They think that that a tension test is truly the ductility of a metal. That's not true. We have to be prepared for extreme situations. The world, of course, the climate is changing. That is important also. We have not to make some idealizations on structures and load conditions. That has, well, that has relation, of course, with this one. Those two are the same things. Also, idealizations on information. Not all informations are real information, are right. Materials in people. There is a real world. Many students don't know that there are inevitabilities, things that the British, for example, call act of God. No one knows what cause. This exists. And to end, a question of human factor. About 20 years ago, the Swiss Federal Institute of Technology made a study with 800 consultants, engineering firms, and they discovered that 36% of all structural disasters were due to engineers' lack of knowledge. Engineers' lack of knowledge. That's brutal, I think. Well, I thank you very much to hear me, and I would like to ask you, Professor Dennis, about first of all, which engineering, which kind of engineers, which course of engineering in France you study welding technology? In which one? Mechanics, materials?
In France, we have three kind of engineer who will be welding engineer. The first one is the entrance from mechanical. They have mechanical base and they learn welding. The second part is material engineer. They come from material, from steel and on, and they enter in the welding by welding metallurgy. And the third part is people from electricity. Because as I said, more than process in welding are electric, and some engineers come from electric parts, and they discover welding through the electricity. But now, in 2023, I said in welding engineers there is 4 parts. One part is processes, understand the processes, generator and so on. The second part is metallurgy of welding. Understand how the metal will move and so on during welding. The third part, and you talk about that, is the design. How you have to design to prepare, to make the welding. But the most important thing that everybody forget is the fourth part. The fourth part is standardization and quality. It's very hard in welding to say after the weld if the weld is good or not. To control welding, you have to make NDT process, radiography, ultrasound, and it's very expensive and very complicated to do. So, to be sure, I don't like the term sure, to have a best quality, you have to make quality before. What I see in quality before is you have to make WPS, welding procedure specification. You have to make a weld with 2 pieces of metal. You have to prove it in with cutting, tensile test, and so on. You are notice all, and you think about repeatability. And the idea is to say, if I make exactly what I done before during the first process, my welding will be good. And all the standard now in welding is based on this system. You have to prove before you can do, and after you repeat. And the second part, you repeat with a qualified welder. Because if you have a good procedure, but you say someone, he can weld, he can make a good weld, and you have to qualify a welder. And the big part of the welding now is to control that you have good qualification, good welder, and to apply that in the technique. And when he said that 36% of a problem is lack of knowledge, I think about that, because most of the bad engineer repeat the procedure without understand what they done. And at this time, you have 30% of problem. Because they repeat like a monkey. I repeat exactly what I done. And what we try to do, because we try, is to have an engineer who can reflect it and not repeat. It's writing that, I make that. It's why I make that. Why is writing that? Just an example. After welding, we make hardness control. The standardization stayed for no more steel, carbon steel. In any place, you must have minimum 350 Vickers. Okay. If you are more than 315 Vickers, the welding is no good. Why? Because in the mind of people who write this standard, if you have more than 350, you have risk of quench. If you have risk of quench, you have risk of cracks, and so on. That the engineer must understand. When he makes the hardness, he find 351, maybe it's good. But you have some engineer, monkey's engineer, I say it, is writing 315. Why? It's writing 315. And they don't know why it's writing 315. And when you talk about that, about 36% is exactly this case.
I think also that there is there are many problems, but one of them, and some engineers think they know welding technology, knowing only one of those areas. That's impossible. You need to know all those areas.
We never know.
Yeah, no, we never know nothing. But you need to have studied some all those three areas minimum. Here we have NDT also as a class, but it's a class in the course of mechanics and metallurgy. And I don't know if Matthias has. Is there anybody from Matthias engineering here? No. No. In materials. It's non-destructive tests. Obliged. Optional. Okay. But mechanical and metallurgy, you need to have NDT. NDT, for people that's not from the area, is non-destructive tests. X-rays, ultrasonic, as Professor Dennis said. Then let's Dennis see.
So,
okay, and I have another question for you. I think you had an idea how we teach weld here. What do you think about the way we teach welding?
I think we have the same one all over the world, and for that, IIW program is very interesting.
Okay.
You don't belong to IIW program, but you have the same mind.
Yes. In the past, about 15 years ago, we tried to take here, to have a IIW course. I organized it, but it was almost impossible. You know that I'm not a bureaucratic man. I cannot work with paper and things. I don't like this. And the problem is that the amount of papers that I had in the past to do here, you don't imagine. And then I gave up. It's not for me. And I've got all course prepared, but I couldn't take here again.
Okay.
Okay.
Ivan show you some material from Brazil. So I prepare a small slide from material in Montpellier we have. Maybe you can make the first, yeah. I will show the. So here's a welding workshop we have in Nîmes. Is a welding shop. Just to show you, we have a submerged arc, as he said, spot welding, flux core arc welding, that is very used in America and in Africa too. We have 6 SMRW, new generation, very small, a water jet cutting from 1 meter to 1 meter. We can cut metal without heating, and it's very interesting. Do not transform the metal. A small mag robot welding, like you. Cutting, forming, oxy-fuel cutting, plasma cutting, a small table of plasma cutting. No, this one is not underwater. No, we can, but it was too expensive. Yeah. Yes, we cut underwater with 2 centimeters of water. Oxy-fuel welding, orbital TIG to weld tubes. We have in research warm manufacturing, 3D printer by welding. Welding arc additive manufacturing. And we make 3D printer with welding. And we work about in research about mechanical characteristics from this kind of structure. GMR steel and carbon steel, new generation, old generation. The last generation of a GMR machine from use, GMR mini. Here you have a system to record it, all the parameters during welding. The student weld, and we recorded all the parameters on the computer, and student can see all the parameters and what's happened during the welding. And all can be recorded to make, again, to repeat what to do. That's the GMR new generation, the new one. GMRW, GMR saving parameters, GTRW, TIG, new generation, all generation of TIG, Tiger process, if you know. A small plasma welding. Oh, we talked before about high density of energy. With plasma, we try to have arc, but concentrated. With the mechanical system, the arc is concentrated. We have more energy in the same surface. GTRW. We have an electron beam machine, a small electron beam machine. Yeah. And we have a very expensive machine. A vacuum furnace to make brazing, for example. A tensile machine, I write old. She's old, but maybe is the best machine that I know. Because the student see. During the test, he see here. He see what's happened. He see the pen. He see really what's happened. A hardness machine, a small furnace, a microscope like yours, with a polisher to prepare the machines, a Sharpie test, really not a bigger than you. Yeah. A tensile machine, new generation with a computer. You don't see anything. You see a computer. A big 49, 50 tons tensile oil machine. It's very interesting to make bonding in welding. We make a high thickness, more than 10 millimeters tensile. And for 40 ton, when you tensile 40 ton, is very impressive. And I don't know if you go, it's a small link. I don't know if you can go. A film we made in Polytech to present a laboratory, but welding goes, data computer is more complicated. Maybe maybe on my computer. Yeah. So that part in Nîmes. So thank you, everybody. If you have any questions. Why not?
Do you want to?
Good afternoon. Thank you for being here. So now we have speak of Professor Leticia Palmade from Food Science, and after her we will have Giovanna Mercalli. She is from ICTA, URGS, but she's now at the United States, so she will give her talk online. Okay, thank you for being here. And after Leticia, you can some questions if you need.
Okay.
After. Thank you, Leticia.
Thank you. Thank you, Naira. Thank you, everybody. Well, hi. Good afternoon. So it's a pleasure for me to be here and to give you an overview a basic overview of what the role of water in controlling food spoilage and quality. So I'm Leticia Palmade. I'm full professor at the University of Montpellier, and I teach food sciences at the Biological and Food Engineering Department of Polytech Montpellier. Polytech Montpellier is an engineering school in France. So, okay, and we will be happy to welcome students from Brazil also in this department. So some words to introduce also foodstuff. What are the main characteristics of foodstuff? Foodstuff are characterized by a great variability in composition, but there are also living systems or systems from living organisms. Foodstuff are also thermodynamically unstable systems. That's why foodstuff cannot be conserved. You have to process foodstuff to be conserved, to be transformed, and so on. Why? What are the main causes of food spoilage? In fact, foodstuff are spoiled by microorganism development, but also by chemical and biochemical reaction. I think everybody, or I don't know, everybody know the main reaction or not? Lipid oxidation, enzymatic reactions, but also non-enzymatic browning. If you don't know what I'm talking about, no problem. I give you a little remember of what are the main spoilage reactions. So we can start with lipid oxidation. Lipid oxidation is microbial spoilage. We can start with microbial spoilage. So everybody see a lemon with this kind of spoilage and so on. The contamination of foodstuff can be during harvesting or during transformation stage of foodstuff. It can be an endogenous origin. It means that the microorganisms are from the animal digestive tract or from an infectious spore in the animals. But it can be also exogenous origin. The microorganism can come from human, animals, water, all the environment. And what is important is the microbial profile of the contamination depends on the food composition, of course, but also on the methods and the environment when it is processed. It is very risky to eat foodstuff with microbial growth. What is your opinion? It is risk for the health or not risk for the health? Yes, Sean, could you answer? Yes? You eat a lot of product with microbial, not contamination, but with microorganisms. When you eat cheese, when you eat yogurt, there is microorganisms. No? Yes. But in the case of contamination, you can have a degradation of the foodstuff. It can be a modification of organoleptic properties, taste, color, and so on. But if you have pathogenic strains, yes, there is a big risk. There is a risk of food poisoning. There is a risk of collective food intoxication. So yes, it is important to control this kind of contamination, of course. Now, talk about lipid oxidation. So lipid oxidation is a complex chain reaction. The objective is not to to learn all the steps of this reaction, but to understand what are the main risks with this reaction. So it is the reaction that occur in high-fat foods. And it is a complex set of decomposition, polymerization reaction. It involves unsaturated fatty acids, and you need dioxygens. But there is different ways to have lipid oxidation. It can be favored by light radiation, but also transition metals. We have also some enzymes like lipoxygenase that are involved in lipid oxidation. How do you know that your butter or your fish is oxidized? How do you know? What is do you know? What? It changes of color? It can be, but it's not the smell. Yes, there is rancidity. You have a modification of organoleptic properties like rancidity, undesirable flavor. It can change the color, but it's not the main effect. But there is also a decrease in the nutritional quality because it's an oxidation. So what will happen if you have vitamins? The vitamins will fight against this oxidation. So you lost the antioxidant capacity of your products because the antioxidant compounds will fight against the lipid oxidation. Are you going to die if you eat some oxidized lipid? No, not today, not today. But yes, it is a risk, but in long term, because the consequence is the production of compounds not recommended for health. And if you have the habits to eat oxidized butter, chips, and so on, yes, in 10 or 20 years, perhaps we can have some problems. But tomorrow, no. So it is also an important reaction to be avoided in product. Or a big family of reactions that are involved in food spoilage. It is non-enzymatic browning. As the name of this reaction is indicated in the name, you are going to produce some components colored brown components. The famous example of this kind of reaction are the caramelization, when you use sugar and how to make caramel? Nobody? Don't be shy. I don't going to. It's not an exam, you know. It's just to be interactive. You need sugar, yes? Yes, yes. So you need sugar, you need water, and you need heat. So it will be a reaction with a high energy activation level. Perfect. And the other one is very famous also, is the Maillard reaction. Maillard reaction is very complex. Do you know Maillard reaction? Do you know every step of Maillard reaction? I give you a medal. I give you if you know that. Okay, so I think it's important to know what is it. If you are a chemist, yes, you can know every step of this reaction. But now what is important for us is the consequences of this kind of reaction. So, as I told you, it group various complex chemical reactions and so on. The substrate of this reaction are carbonyl compounds, sugar, reducing sugar, but also ascorbic acid, vitamin K, products of lipid oxidation, and so on. And it needs it. And what is important, it can be a desired reaction. In some processed food transformation, we need this reaction to develop aroma test. For example, in all the roasting processes of coffee beans, cacao, the roasting, the baking, the beer, the whiskey, the color of this product, the brown color, comes from Maillard reaction. But in other case, it's not desired at all. For example, when you sterilize milk, you don't want to have brown milk. You want to have a white milk. When you concentrate fruit juice also, you have to avoid this reaction. What is the consequence of this reaction? We have a decrease in the nutritional quality, because during this reaction, you have a polymerization between reducing sugar and also essential amino acids, in proteins. So we have a loss of essential amino acid in foodstuff. You have also a reduction of protein digestibility due to the polymerization between all these components, and a modification of the antioxidant capacity of the food. Are you going to die? Not today. Not today. Perhaps in 10 years or 20 years. But Maillard reaction, caramelization is not so dangerous, but Maillard reaction leads to the production of potentially toxic and mutagenic compounds. So be careful with roasted meat and so on. Okay, the last reaction I want to tell you about today is the browning enzymatic reaction, browning reaction. The consequence is also the production of brown colored pigments and so on, but do you need it to make that? No, you only need polyphenols in fruits and vegetables, and you need dioxygens. So it's an enzymatic transformation in the presence of dioxygens, and is a transformation of phenolic compounds into quinone, then into colored polymer. The enzyme involved is polyphenol oxidase, and we need also oxygen. You are going to form color pigments, melanins. They are often brown or black, but they can be pink, red, and blue. As for non-enzymatic browning, it can be a desired reaction. For example, for a desired reaction is in green. In the ripening of dry fruit, dates, grapes, in the fermentation of tea, coffee, cacao, we can develop this kind of reaction to develop the color of the product. But when you cut your apple, when you cut your avocado and so on, you don't need to have a brown guacamole. You know what is guacamole? No, it's green, it's not brown. So you want to avoid that. And you have to fight against this reaction in this kind of product. So you have a modification of the organic properties of phenolic compounds, color test. Is there a risk for health? No, not really. So the modification, you have only a modification of the antioxidant capacity and the property of phenolic compounds, but you are not the risk of diseases or intoxication and so on. You can eat your brown apple, you can eat it. You are not going to die today. Now, come on, back to water. What is the role of water in all this reaction? We are going now to make a focus on water in foods. This is a famous pyramid of which is representing the content of water in foodstuff. In foodstuff. There is here the composition, the content of water. So what we can say at the basis of this pyramid, what we can say, the majority of the basis of this pyramid is raw product, is non-processed foodstuff products. And except for oil and grains that are at the top of the molecules, then you can see that there is a relationship between the content of water and the degree of processing. It means that decreasing the water content in food improve the stability in food. So I think it's not a news for you. It is very, you know, our ancestors discovered that also. What they did to conserve raw materials, our ancestors. What they did. Tell me some processes that they used to, tell me. Salting? Yes. Salting, another one. Drying, of course, drying. So based on empirical knowledge, they already know that reducing water improves the stability of foodstuff. Why? We are going to show why. First, water has different major role in functions in foods. If you eat a very good apple and an old apple, you see the difference, of course. The water content have an impact of the turgescence of vegetable cells. So the water will influence food texture and appetence, of course. The tenderness of meat is directly related to the content of water. But water, what is important is the water is involved in all reactional state of water. Do you know how to measure the reactional state of water? I will give you the answer. Wait a minute. So, what is important also is that water, a part of the water in the foodstuff, in the product, is bound to micromolecules. The molecule of water it's a very particular. It has extraordinary properties. And she can have the molecule of water has the capacity to decrease the attraction between two ions from opposite charges and to surround the polar ions and groups by strong electric interaction. So the affinity of the molecule towards the water will depend on the polarity of the macromolecules and also of the chemical bonds and functions present in the macromolecules. So we can define here the degree of polarity. Here you will have a strong bond between water and the molecules and ions. And here, with, for example, lipids, there is no link, very few links. And what is important is the bond between water and micromolecules will lead to a modification of the water properties. When the water is linked to proteins, it's no more available to be a solvent, to be frozen, to be evaporated. So we have a decrease of solvent properties, a decrease of chemical reactivity of water. Okay? So we can now answer we can measure the reactional state of water. Do you know what is the tool? What is the Sean? I think you know because Sean has my courses in French last semester. Do you know what is how can you measure the reactional disponibility of water? Sean knows, a student, of course. Do you know? Yes. Perfect. Thank you. Yes, water activity. Water activity is an important tool for food scientists. Are you going to be a food scientist? No? You are going to, yes? Yes, yes. So, if you are going to be a good food scientist, you should know what is water activity. You should know. So, water activity is, in fact, what is it? Is the ratio between the water pressure, the partial water pressure in a food product, and the partial pressure of pure water. When you took pure water, all the molecules are free and are very, very free, and it's very easy to be evaporated at the interface. So the partial pressure is very high. But when the water is linked, is bound to micromolecules, water is not free, no more free. So the pressure applied by the water molecules are less than here. So here you can measure the water activity, which corresponds to the reactional availability of water. And what I want you to remember here is, if you want to know if a product is stable or not, you don't have to only consider the moisture content. Moisture content is important, but it's not the good parameter to know if the product is stable. You should you should consider the water activity. For the same moisture content, you should have different water activity. Why? It depends on why, on what? It depends on the composition. If in a product you have a lot of salt, you have a lot of sugar, the water will be bound to these molecules and the water activity will be low. But if in your product you have the same moisture but you have lipids or less polar molecules, the water will be more reactive and more involved in food spoilage. Okay? So what is important to know, that the water activity is always between 0 and 1. At the equilibrium, it is in equilibrium with the relative humidity, ambient relative humidity. And as I told you, is an important parameter to estimate the stability of a foodstuff. Food scientists have defined three areas concerning this water activity. When a product has a water activity below 0.2, 0.3, we talk about strongly bound water. What is this water? It's the water of the monomolecular layer. It is the first molecules of water bounded to the micromolecules. This water is not available. No solvent or reactional properties. This water has a high absorption energy and no molecular mobility. Okay, it cannot be frozen. It can be evaporated, but you have to involve a lot of energy. When you have water activity in this area, we talk about weakly bound water. It is here. It is this hydration sphere of water here. And what is important in this water this molecule have a solvent and a reactional properties. Then, when the water activity is above 0.75, we talk about free water. So, of course, this water is the main part of non-processed foodstuff, of course, is the water retained in meat, in gel, and so on. We talk about free water. So, when you measure your the water activity of your product, you can see if you have strong bounded, weakly bounded water or very free water. So, of course, there is a link between moisture and water activity. As you can see here, very low water activity concern mainly dry product, of course. But here, for non-processed product, you have a very high water activity, of course. But we are not going to eat only dry product. The answer could be, I want to stabilize my product, I'm going to dry everything. Okay, fine. It's like, you know Thomas Pesquet? He's a famous French astronaut. Astronaut goes to the spatial station, like that. So Thomas Pesquet is eating every day drying product. And I think it was happy to return to Earth and to have a Big Mac, or I don't know, a McDonald's, or to have a very soft and with a high moisture content, you know. So what is the solution to decrease water activity in food? It's not only drying. You can add some depressant agents like sugar, salt, sorbitol, glycerol, and so on. So there is a list, there is a number of depression agents, if you look at the literature, but only few can be used for food stabilization. Because when you use salt, you are going to change the taste. So you are not going to put salt in jam, for example. You are not going to put sugar in your, I don't know, in your meat. So, in fact, there are very few ones that are very effective, efficient to reduce the water activity in foodstuff. There is a good correlation also. What is important is that Labuza in the next century find a good correlation between the food spoilage rate and the water activity. Here you have the main degradation reaction I presented you at the beginning of this presentation. Here you have the microbial growth. Here you have lipid oxidation, Maillard reaction, enzymatic activity. What we can see? We can see that if you consider microbial growth, it's very easy to limit the growth of microorganisms if you decrease the water activity of your product. And you can see that if you reach 0.7 here, I think you are quite very stable concerning the microbial growth. It can be reached by drying, but not only by adding some depressant agents. Okay? Look at the enzymatic activity. The enzymatic activity also is going to increase when the water activity is above 0.5, 0.6. Okay, it means that when the water becomes very become free, of course, the enzymatic activity can increase. What I want you to remember is the shape of these two reactions, lipid oxidation and Maillard reaction. What we can see? We can see that even if we are at low water activity, we can have lipid oxidation. Wow. So what is the solution for lipid oxidation? Guess, have you guessed to tell me how to reduce lipid oxidation at very low water activity? What is this reaction needs? Lipids, of course, but also dioxygen. So you are going to put the product under vacuum. Okay, that's why a lot of fish and so on are stored at even frozen. They are stored under vacuum packages to avoid the presence of dioxygens, to avoid oxidation of lipids. So it was this. What is important also is this area. You can see that if you want to decrease the rate of lipid oxidation, you can process you can formulate your product to be in this area of water activity. You are going to minimize this reaction. Another things to be pointed here, to be focused, is Maillard reaction. Maillard reaction, you can see the maximum rate of Maillard reaction is at the intermediate water activity. When you, for example, concentrate your milk, when you concentrate a fruit juice, what you do when you concentrate? You take off water. It's okay for everyone? So, you are going to decrease the water. You are going to decrease the water activity. But if during the process you go slowly in this area, or you decided to, as you saw that for microorganisms 0.6 was enough to stabilize your product, or I'm going to stop my reaction, my concentration at the water activity of 0.6. Oh no, it's not a good decision because you will be at the maximum rate of this reaction. So as you can see, this diagram is a very useful tool for you to predict the stability of your product, but also to master your process, okay? Another tool what is important for future food scientists is the sorption isotherm. What is the sorption isotherm? Is the relation between the water activity and the water content of a product. And as we can see, we have a curve. How it is determined? You take a product. For example, you take a dried product and you build the adsorption curve. It means that you add water and you measure the water activity. And when you do the inverse, you dry a wet product, we talk about desorption curves. Why it is important? First, talk about hygroscopicity. What is hygroscopicity? Is the influence of the change in the ambient relative humidity on the water content of a product. And you can predict this hygroscopicity when you look at the shape of your sorption, the sorption curves. Look at that. For example, it's a raining day. Oh, like today. It's a raining day, so the humidity in the environment will increase. At this equilibrium, you will have an equilibrium between water activity and the relative humidity, the ambient relative humidity, if the product is not in packaging, of course. So look at the product in green. What happened? This increase in water activity, it means in partial pressure and so on, will have a very low impact on the water content of the product. But if we consider this product, the red product, the same increase in water activity will have a big impact, a high impact in the water content of the product. It's the hygroscopicity. Everybody in his life saw a sweet, some crystal sweets. You let a sweet on the table and it's a raining day and you come, it took a lot of water. When you talk about powders, some chemical powders, you have just to take the powders and quickly close the box because it's going to take a lot of water. It's the hygroscopicity. So it is important. And it is also one way to say, I need to package my foodstuff because it's going to take the water, all the water of the room, okay, and it will be not stable. Another things to be noticed on these sorption curves is the hysteresis. The hysteresis is, as you can see, in the intermediate water activity area, the curves of adsorption is not the same that the curve of desorption. There is a lot of product presenting this hysteresis. And what it means? That means that a product for the same water content, here, imagine you have this water content. If you have you can be here. For the same water content, the product will present a water activity less important than if we are in the adsorption curves. The product is more stable if it's desorbed as compared as rehydratation. Okay, so it is also an important fact to be noticed because, for example, you produce a powder, you are very happy because you are in a very stable, here you are very stable and you are very, very happy, you have a very low water activity. Took this one, is more representative. You are happy, you are at a low water activity, the product is stable. But it's not, the product is not in the packaging and it is quite hygroscopy. and it took a little bit of water. What happened? You change the curve. You are now in the curve of adsorption. You are no more in the curve of desorption since you are going to take water. And as you change the curve, you have, for the same water content, you have a higher water activity. And then here, your product is no more stable. Okay? So, as I told you before, like hygroscopicity, hysteresis of the sorption isotherm will show you if you have to protect your product from moisture, from environment moisture, and so on. And it can help you to design a packaging also. Okay, so just to show you that the isotherms are also, the water activity will increase with temperature also. If you have a product and the temperature, the ambient temperature increase, the water activity of the product increase. Okay? So if the product is not in the packaging, what happens? The product is going to be in equilibrium with the environment, and you will have some drying of your product. But if the product is in the airtight packet system, so it cannot be in equilibrium with the environment. So you will be in a very critical area because you will have an increase of the water activity in your packet, in your packaging. So the same thing, these curves, this sorption isotherm, will help you to define the stability during the storage and what happens when the temperature increase, decrease, and so on. It's very powerful predictive tools for scientific also, but for food technologies. And the last things I want to tell you about water in food is I want to talk about glass transition in food. Do you know what is glass transition or not? Why your snack for during you drink at the bar and you eat some snack is very crispy snack, and if you let the crispy snack on the table, it's raining. What happened to your crispy snack? They are becoming soft. Okay, no more crispness. What happened? It's glass transition. It's the glass transition. Glass transition it should be considered only for dry or frozen product. If you have milk or if you have non-processed meat, don't talk about glass transition. No. Glass transition is a particular state of macromolecules in dry or frozen product. When you dry rapidly a product, when you decrease rapidly the temperature and the content of water, what happens? For example, you dry a biscuit, you dry a powder, you are not in a crystal state. You should be normally in a crystal state. You know, when you dry a product, normally you have the curve of solubilization, and when you cross this curve, you should be in a crystal state. But if you cross rapidly this curve, you are not in a crystal state, you are in a glass state. And it is correlated to the crispness, the texture is very correlated to the texture of the product. When this state is not stable, the crystal state is thermodynamically stable. The glass state is not thermodynamically stable. And this state is characterized by a temperature of transition. What kind of condition can occur when you cross this temperature? You became a rubber. You shift on the rubber state. So if you want to keep your product with the crispness, when you want to keep your powder stable, you have to be the storage temperature of your product should be very far from this temperature. Okay? But what what she told about that. What is the water problem in this in the water transition? The problem is that the water is going to decrease the temperature, the glass transition temperature. It means that you at the beginning you have a snack, you have a powder, you have a sweet, very nice, very like a glass, very crispness and so on. And for example, the temperature of glass transition is 60 degrees, and the storage temperature is 20 degrees. So you are far from the transition, so it will be okay. But if this product is going to take some water, if the content of water increase in this product because it's not packed, it's not protected and so on, you have a decrease of the temperature of glass transition. And then your product will be very in danger. The crispness of your product is in danger because you can cross, the temperature will go under the temperature of the storage. That's why you can have glass transition in a lot of products if you don't take care of water and if you don't protect them. So in few words, the glass transition is a reversible transition. There is no heat absorption or desorption. It's a transition of the second order. Transition of the first order are evaporation, frozen, and there is heat activation and so on. Here, there is no energy involved. It's a transition, a reversible transition from a brittle glassy state to a plasticized rubbery state here. And this state is characterized, this transition is characterized by a temperature. And there is a rapid modification of the physical, mechanical, electrical, and thermal properties of your product. There is an abrupt modification of free volume and so on. And as I told you, this temperature is strongly affected by water content. And what is the problem in food stability and so on? When you have powder, you can have a collapse of your powder. When you open, or when you open, for example, milk powder, and you let your milk powder open, I don't know, 1 or 2 weeks or more, then, and you come back and you see you are no more a very nice powder. You have some blocks like that. What happened is glass transition. The glass transition of the lactose present in milk powder, for example, you are going to have a sticky, the formation of sticky surface, since you change the state of your product with or without caking. You have a collapse of, you lost the porosity. You have also the release of volatile compounds and the softening, a loss of crispness. I don't know if I have time to show you that, but this is a relation between sorption isotherm and glass transition, just to show you how to manage, how to use these tools. For example, when you make biscuit, or when you make some like that, when you cook this kind of products, you want that your biscuit are cracky biscuit, crispy biscuit, you know. But here it is the sorption isotherm of gluten, okay? But gluten, the relation between water and gluten, is not directly said to you if your biscuit will be crispy or not. You know, it will tell you is stable or not. Stable against reaction, chemical reaction, biochemical reaction, microorganism growth, but it's not going to tell you if you are going to keep the crispness of your product. So we have another tool, is the relation between the temperature of glass transition of gluten as a function of water activity. It is this curve. You can see when the gluten is quite dry, only dry, the temperature of its glass transition is very high, 200 degrees. And when the water activity increase, it means when also the moisture of the product increase, a strong decrease of of glass transition. So what we know, crispness of your biscuit below this curve, okay? So when your product is stored at ambient temperature, as you can see, I took the Brazil ambient temperature near 50, okay, for my example. So when the biscuit, when your biscuit is stored at ambient temperature, blah, 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 you can read here the critical water activities that not be crossed. You should not cross. You should not cross the water activity because you will be above the temperature of glass transition. So your biscuit, poof, will be soft, okay? But it's not very easy to have in your cook or in your industry something to measure water activity and so on. What you measure is, when you formulate a product, you consider the quantity of water you had. So you mixed the both curves, the both tools. We mix the tool glass transition curves here, and here the sorption. So as we saw with these curves, we determine the critical water activity to keep the crispness, and when we report the water activity on the sorption isotherm, PAM, you can find the critical water content that not be crossed. For example, when you cook, we are in a company that is producing cookies or biscuits, and you have to determine, to master the cooking step. I have to cook, to dry, doing the cooking, the drying of the product, of course, and you have here the critical value that not be crossed. You should cook your product to be here, okay? And if you be here, your product should not be crispy and so on. Okay? It's an illustration of how you can use these useful tools to master the stability and the quality of your product. So to conclude, I just want to say I just want you to remember that the role of water in food is complex. So you know. The stability of food products depends on the reactivity of water. So you are going to use the water activity tool, the sorption isotherm and so on. And also it depends on the molecular mobility of water in these matrices. And so you will consider also, you have to consider also the glass transition of biomolecules in foodstuff. So you have two tools. You have water activity, that is a thermodynamic parameters. It can predict the amplitude of water transfer between the two heterogeneous zones and so on, and it can be used for all the products. Okay, low water activity or high water activity, and concerning dehydrated or frozen product, you should take into account what happened concerning the glass transition in your product. If you want to keep the texture, the properties of your product, and it is a kinetic parameters in contrast to thermodynamic parameters. Okay, that's all my talk. Thank you. No question. And just a remark, as you can see, food science is very near material science, in fact, because glass transition is a big issue, is something very important in polymer sciences. And often, we use the same scientific approach between food science and material science. And if somebody say, oh, you are a food scientist, or you cook products. No, you are not a cook. You're not a cooker. You are a real scientist, and you use the same tools than material sciences. I say that because I have a specialist of material sciences here.
Thank you for stressing all these similarities between food science and material science. So, of course, I want to ask you a question in this direction. Can we measure water activity using spectroscopic techniques like infrared spectroscopy?
water activity is measured using, it can be measured like spectroscopy, but is measured with AW meters, and you use equilibrium. You take a foodstuff, you put in a quite vacuum area, and you decrease the temperature. It means that when it will appear some drop water in, there is a mirror, you decrease the temperature, and when some droplets of water appear on the mirror, you notice the temperature. This temperature, it's the temperature when the vapor, partial vapor, it became saturated. So with the tables of water, and you have the partial water pressure, the partial pressure water in your product. It is commercial systems.
How long is it?
5 minutes.
Okay, maybe spectroscopy is faster. We'll
But
talk about
it's
it.
cheaper.
Questions? And now we have Giovanna Mercalli from ICTA.